Moving on to our last session for the day on model-based calibration, engineering enhanced models for engine and ES system to enable virtual testing in MIL and HIL environments. I would like to request VP Director, AVL India Technical Center, Emmanuel Salin, to kindly join us on stage.
The other one, I would like you to explain me how it works. So it's okay, ladies and gentlemen, good evening. Thank you for staying until there. Try to keep interesting until the end. This is the last session, as I understand. So I will talk today about model-based calibration, to be simple. Basically, this is a methodology that we develop in AVL that addresses most of the customer challenges. What are we talking about? New legislation in automotive industry has CO2 limitations, so you know the Paris Agreement, real driving emissions, in-use tests have increased totally the complexity of the development of internal combustion engines and drivetrains. Here you have a passenger car figure, but it could be a commercial vehicle, it could be an on-road application, it's the same. We'll have to emission legislation under diverse operating and environment conditions. So the effort required to calibrate that, to achieve an adequate system and calibration validation is just huge. The conventional development process that you all know require application of huge amount of manpower, test equipment, and budget to reach these targets, particularly when considering that, in fact, most of the validation is based on real prototypes coming quite late in the development system. So links is to, I heard at least 20 times the word front loading of the right V to the left branch of the V cycle. Of course, this is easy to say, but how can you do that? Basically, the message is the limit of efficiency has been reached with conventional models, and we need new approaches. So what do we propose in AVL? This is MOBEO, so model-based emission engine optimization. It's based on a method for model-based development throughout the drivetrain development. It's based on a powerful, real-time, semi-physical engine model. Basically, you totally replace the engine plus the after-treatment system by a model. So for the calibration engineers, you use exactly the same suite of softwares, tools, when driving a normal engine or driving a model. So you have a complete uniformization, one-to-one comparison between what you're simulating and what you see on the engine test bench. The key for this method is to have an accurate virtual representation of the combustion engine. So I'm talking here real-time and accurate. This is the two main words. So semi-physical model that we develop. Physical models are well representing reality, but you cannot use them everywhere because they are slow. Empirical models are very quick, but not sometimes representing reality. So we use physical model when possible and fitted, I would say, fitted on the engine empirical model to come to a semi-physical models. So basically the combustion, for example, crank angle degree, you can forget it, and we have semi-physical model for that. I would here just to say that I'm talking about the engine and after-treatment parts, but the whole system can be replaced by models. So you can have the vehicle part, in which you can simulate the road load conditions, the driver, how is he aggressively driving, or more, less, I would say, on a passive way, of course, the gearbox and the tires and link to the ground. All that can be simulated. I won't talk about that today. I want to focus on the engine plus after-treatment system. So this is how it looks like. In fact, you have the virtual testbed configurations. So the real-time models are here compiled, stored on the hill. So virtual testbed, or hardware in the loop. And on the left side, you have the comment, really, that it's completely the same as you have in the real-time testbed. So this is the, I would say, the USP in the system in which you keep completely the interface to the model or the engine completely the same. So for the, once again, for the calibration engineer, doing with this environment or doing it from an engine testbed, it's exactly the same thing, is using the same tools. Is it accurate? So I'm going to walk through to actual results. So this has been obtained for a commercial vehicle engine, European application. So this is steady state comparison, where you have actually measured points and simulated one. So you can say it's pretty good in steady state. In transient condition, this is the temperature modeling along the EIS system, which is critical for a commercial diesel engine. So with DOC, DPF, and SCR injection. This is the temperature profile, so you can see it fits pretty good. And also this is emissions. So you have speed and load profile, and in red and blue, you have actually the NOx. TP is tailpipe, so the NOx that you have and you actually measure during a test. So you can see that the second to second cycles and what you get at the end of the bag is fitting pretty good. Where can be used the model-based application? This is to represent globally what a global development cycle is, so from the concept simulation to the customer and the start of production. In fact, you can use it everywhere with different level of refinement. You can use it in the concept phase. You can use it during the calibration phase, so once you've frozen the concepts and the components. You can use it just at the end for robust tests and fleet validations, when you actually validate the cars, and also for post-SOP support. For example, the model will have to be refined according to these steps, but you can use it everywhere. I put there some examples on how you can use it. So in the concept phase, you have benefits in concept risk, in which you can evaluate different concepts before actually choosing a hardware. So thus reducing the engineering loops where you don't have the hardware. In the time of calibration, you can also link it to the control and software development. Since you have a model, you can choose between different strategies on how to control the functions. Check it initially and also make initial calibration on it. On the calibration, you can use it even without having strong related hardware, for example, to simulate, I don't know, half clubbed EGR circuit that you can hardly do it physically. On a simulation and hardware in the loop system, you have no problem to simulate it. One also big benefit near to the end of the calibration process is about the robustness investigation, in which you can simulate a lot of conditions that you cannot represent on the road. You can, for example, 40 degrees, 2,000 meters, aggressive driver, how my system will react. Did I calibrate my OBD correctly? Will I have a mill going on? This, with the simulation, you can pretty do it, which is quasi impossible to do it with a car. So this is how it looks like. I will go through just one cases. So you have the test bed, in which you can draw parameters to identify your model. Input also coming from the vehicle side. You input that in a model that you run through virtual test bed, and then you can simulate all the different calibrations, environmental conditions, production tolerances, aging effects. You can all that to do with the model. Once again, very difficult to do it on a real car, because either you don't have the components or you don't have the environment conditions. And so all this is run on the concept phase or really at the end on the calibration phase. One example, this is once again real case. This is not example, this is how it has been done. This is the pre-calibration of turbocharger altitude protection. Here you have the input. What we put is the speed and load during going up a hill. This was done in Spain, in Granada, so you go to 2,000 meters, roughly. And along with the altitude, you have the turbocharger protection going on, in which you have to adjust the boost pressure and the injection quantity in order not to exceed the turbocharger limit. So for example, this is used now, completely for every development that we have, we do a pre-calibration with mobile. So you can actually fill in maps. We, of course, that doesn't substitute to the actual testing that will be done at the end, but all the pre-calibration is done completely on the virtual test bed, saving us a lot of time. So speaking of saving, this is, I would say, the summary of what it brings, actually, in terms of number, with now the experience that we have, that we are running the first projects completely. So this is the first application. When you speak to derivative application, it's even more, because once you've done it, it's a lot easier to simulate another car or vehicle with the right engine. But on the first application, we found that it's possible to front-load 23% of the calibration tasks. I don't know if you imagine what it represents, but it's huge. That leads to a cost reduction about the same, 20%. We were able to reduce the prototype of 10% and to shorten the calibration, so the time to market of 3 months, in a period of, I would say, 18 to 2 years. So here, for example, OBD, you see we consider that it represents 22% of the calibration activity. We were able to cut it by 4%. So instead of 22, you have actually 18%. So at the end, that's where I come to the 23% of gain. The main message here, that we have, using this method, that you are able to simulate very early in the process, where you don't have the parts. You are very much precise. You gain in time to market and numbers of activities, so cost. Questions, maybe?
Have you validated this on a BS6 program yet?
We're actually doing it.
Oh, okay.
We use this as a standard process, I would say, for the BS6 development that is going on. No BS6, but we have used it on Euro 6 program that are already on the street in Europe with success. I was speaking, in fact, on the Euro 6 project, and now we bring that to India and proposing to the Indian customers.
And making those sort of savings, yeah?
Sorry?
And making those sort of savings.
We will see, but the order of magnitude is for sure about the same, yes.
Okay, thank you.
Thank you.